Great. Thanks again for coming back. And I want to reiterate Egbert's thanks to the organizers. I know how complicated and stressful it must be to put on a conference during the pandemic, but I'm sure I can speak for everyone to say how grateful I am to be here. So. Okay, so last time we at least sketched the proof of the following theorem, which is that there is an interpretation, or there is a model of homotopy type theory. Homotopy type theory in the category of simplicial sets. So this is Voevodsky's simplicial model of homotopy type theory. In the first lecture, we explained sort of what it even means to come up with a model of type theory and how one would construct a category that's sort of strict enough for this to even be possible. And then last time we were sketching some of the main ideas and showing that this category of simplicial sets has a universe which can be used both to impose the coherence required in the model and also to model the universe of types. And I regret that I didn't get a chance to say more about the univalence of that universe, but that's a fun part of the story. The reason I wanted to start with this theorem, though, is to point out something that's a bit curious about it. So some curiosities. So the first thing is that just what this means. So the interpretation. So what does it mean to say that there's a model, that there's a particular functor, and this interpretation functor is a functor of one categories, so of ordinary categories. Its domain is this category of context built out of the syntax of homotopy type theory, while its codomain, it's more or less simplicial sets, but really it's a contextual category replacement of simplicial sets, so it's kind of an even, stricter version of simplicial sets. And yet, the popular interpretation of this theorem seems quite different. And yet, somehow, this result, this theorem, gives an interpretation of hot in what's commonly described nowadays in the infinity topos of spaces. And of course, as the name suggests, the infinity topos is not a one category, it's an infinity category. It's a weak infinite dimensional category. So there seems to be a little bit of a mismatch. We proved a theorem using one category theory, and yet we're concluding something about infinity category theory. So the first thing I want to do today is explain how an ordinary one category can be equipped with extra structure that makes it present an infinity category, such as an infinity topos. I'll also explain what an infinity category is and what an infinity topos is, and then after that we'll move on to Mike Schulman's generalization of all of these results to arbitrary infinity topoi. Okay, so the point of view that I'm going to take on infinity categories today is like totally not at all the way I would ordinarily think about them. And if you want to hear more about that, Dominic Verity and I have just published a book called Elements of Infinity Category Theory. None of what I'm going to say today appears in there, and kind of conversely. So, but the point of view we're going to take today is designed to prove the theorem that Mike proves about interpreting hot in infinity topoi. And so what I'll explain first is how simplicial model categories can be used to present infinity categories. Okay, so firstly, what do I mean by an infinity category? So here, the term infinity category is really a nickname that Jacob Lurie gave for the purpose of writing his book to what's maybe more properly called an infinity one category. And what that refers to is a category that is weakly enriched in infinity groupoids, aka spaces. So, right. So what enriched means is that in a category we have the objects, but then we also have in an ordinary one category a set of morphisms between any pair of objects. Here, that set is enhanced to an infinity groupoid or a topological space, but we no longer require sort of strict composition. So in fact, kind of the appropriate perspective for infinity category theory is that there's not even necessarily a well-defined composite of two composable arrows. Rather, there's a contractible space of choices of potential composites. So what makes infinity, so I mean, there's a sense in which infinity categories, again, by which I mean infinity 1 categories, are analogous to ordinary 1 categories. There's a sense also in which the theory of infinity 1 categories is quite a bit harder, and it has to do with this sort of weak composition law. Nevertheless, there's a theorem, maybe which I'll attribute to Julie Bergner, and I think for the Quillen equivalence, Jacob Lurie, but I might be misremembering, that any infinity category can be presented by not a weakly enriched category, but a strictly enriched category. So I could say a category that is strictly enriched over spaces. We've seen that maybe simplicial sets are better than spaces for kind of technical categorical reasons. So I'll say simplicially enriched category. So the difference between this notion and this statement is now I mean sort of classical enrichment in the strict sense of ordinary 1 category theory, as opposed to the weak enrichment, which is kind of the moral sense. So what I mean by this is if you have any particular infinity category in mind, like this infinity category of spaces, there exists a simplically enriched category that encodes that somehow. Except I want to make one modification here. One of the things that I've mentioned is not all simplicial sets are sort of equally space-like, because in the combinatorics of simplicial sets, the interval is directed, and if you have a path from x to y, you want to be able to get a path from y to x. So what I'd really like to have instead is a complex enriched category. So this is enriched over the sort of subcategory of those simplicial sets that behave like spaces are the complexes. Okay, I mean, and that's actually what's given in the theorem. So, right. So how would we find a source of these complex enriched categories? So a source of such, I mean, simplicity enriched categories you can kind of stumble on the street, but complex enrichment is a little more subtle, so that's a little harder. A source of such is given by simplicial model categories. And this is a term that I've used a few times as a black box, and now what I'm going to do is open up the black box a little bit, and then I'm going to close it back down again. So you'll see this is a sort of partial definition. Yes? No, depends on who you're talking to. So, and in fact, I don't really, well, yes, yeah, no, but there's a sense in which essentially any model category can be made equivalent to a simplicial one, so you might as well, and that's what we're going to do today. But let me tell you what a model category is first. So, so bi-complete category, bi-complete category, meaning has all limits and colimits, E, sort of has a model structure if it has sort of the following classes of morphisms. So the idea really how these 1 categories are going to present infinity 1 categories is that they're given some sorts of additional structure. And what a model structure refers to is the following. So one of the morphisms are called cofibrations. The notation that I've been using implicitly all along is this arrow with a tail. And if I need a quick name for it, I'll call that class C. The other class is called weak equivalences. So the decoration would be a tilde over an arrow. And the class we might call W. The third class is called fibrations. So the decoration would be an arrow with 2 heads, and the name is F. So when I've been using this notation in previous lectures, implicitly these are probably classes of that sort for some model structure. So there are 2 axioms. The first one is that if I pair together the intersection of C and W, so those are called the trivial cofibrations with the fibrations, or I pair together the cofibrations with the intersection of F of W, these are what's called weak factorization systems. And this part of the black box I'm not going to open up. So I apologize. But the second axiom, which is something that we've used implicitly in arguments, is that W satisfies the 2 of 3 property. And what that refers to is if I'm given a pair of composable morphisms and they're composite, if any 2 of these are in W are weak equivalences, then so is the third. That's a property of the isomorphisms, for instance, and it's a requirement for the weak equivalences. Okay, so what makes a model structure into a simplicial model category? So E is a simplicial model category. So if, moreover, so the first thing I should add is that E is simplicially enriched, tensored, and co-tensored. So this is the simplicial category analog of being bicomplete. So these tensors and co-tensors suffice to mean that you have all simplically enriched limits. And if you don't know what they are, I wouldn't stress too much. Tensored and co-tensored. And then there's one additional axiom that requires that the simplicial enrichment and the model structure are compatible. So the way that I might say this is as follows. So we can consider a particular functor whose domain is an arrow in E, or really a pair of arrows in E. It's going to be covariant in one of them and contravariant in the other. And its codomain is an arrow in simplicial sets. And how this functor works is it takes an I and an F and applies the mapping space, I guess, really to all 4 objects, and that will give you a commutative square. But then it looks at the map from the initial object to the pullback in that square, which amounts to this map by map AY. So a thing that you might note is this codomain here is the simplicial set of commutative squares in the category E from I to F. That's sort of a fun exercise. I think I mentioned at some point the notion of an internal lifting operation. That would be a section to this map. And what the condition is that this functor is right-quillen in a sense that's appropriate to bifunctors. And again, that's a black box I'm not going to unpack for you. But the point of highlighting this is to make the following observation. So what this right-quillen business is giving us is certain conditions under which this map that we have here is a fibration. And we could think in particular of a special case where this A is the initial object and this Y is the terminal object. So in that special case, this object here is delta 0, in other words, the terminal simplicial set. And the conditions that guarantee that this is a fibration apply in particular when this map here is a cofibration and this map here is a fibration. In other words, if if B is cofibrant and X is fibrant, and so that's the corollary. If B is cofibrant and X is fibrant, then this map Bx is a concomplex. And so the whole point of this discussion was to give a source of concomplex enriched categories. And that's what we found is if E is a simplicial model category, and these, it turns out, actually are quite abundant, then the fibrant, cofibrant objects, so if we restrict not all objects, but if we restrict to the ones that are both fibrant and cofibrant, define a complex enriched category. So this is a way to think about the infinity 1 category that is being presented by a simplicial model category. What you do is you use the model structure to identify these special objects, these fibrant, cofibrant ones. And then if you cut down there, now your simplicial enrichment just gives you a concomplex enriched category, and that means it's a category strictly enriched over spaces, so in particular weakly enriched over spaces. That's sort of as much as we need to know about that. Maybe just one aside, this we won't actually need, but I mean, it seems a little weird that we have this model structure and then we just kind of use it to throw away some of the objects to extract this model category. But the objects that we've thrown away are somehow still present in this following sense. So there's this notion called the homotopy category of a model category. So the homotopy category of E is, so a way to understand it is to just kind of formally invert all of the weak equivalences in E. So this is an operation that you could perform more generally on any one category with any class of weak equivalences, but the model category axioms guarantee that this is sort of well behaved and you can kind of control what this category is. And this homotopy category and is equivalent to the category of, so I could just take my objects to be the fibrant, cofibrant objects, fibrant and cofibrant, and I could take the Hom spaces, maybe let me say from a B to the X to be pi naught of these mapping spaces from B to X. So this category that we're mentioning here that presents the infinity 1 category with the fibrant, cofibrant objects as the objects and the Kahn complexes as the mapping spaces. If we take path components of each Kahn complex, that gives you a set, and that's the homotopy category. So this can really be understood as an enrichment or maybe an infinity categorification of the homotopy category. Yes? Right, so what Harry knows is that there's other ways to define these mapping spaces even if you don't have a simplicial enrichment. They're more complicated, so I think that's related to the question. So this is not necessary technology, but I'm giving it to myself to make my life a little easier. Great, so there is an comment that's sort of worth making. So what I'm trying to explain is that simplicial model categories present infinity categories, but the infinity categories that are presented by simplicial model categories are special in the following regard. So the infinity cats that are presented by simplicial model categories are special. So I argued that, or I claimed anyway, that any infinity category can be presented by a Kahn complex enriched category, but there's something special about a Kahn complex enriched category that comes from a simplicial model category, and that has to do with these tensors and cotensors and this bicompleteness. So in other words, part of the requirements of being a model category is that I have all limits and colimits, and that's a special property of an infinity category. Like an ordinary category, sometimes you have the limits, sometimes you don't. So they have all. So in the terminology of infinity category theory, you would just call these limits and colimits because there's no other competing notion of limits and colimits. But in the simplicial model category, so that presents it, these are presented by something called homotopy limits and homotopy colimits, presented by homotopy limits and homotopy colimits. So as Pierre-Louis knows, I would love to just spend an entire week discussing homotopy limits and colimits. It's a beautiful subject, and there's quite a lot to say about that. But I guess the reason I'm pointing this right now is I want to make the following definition, though maybe before I do so, I should mention an example. So there's one example of a simplicial model category that we've seen thus far, and it is, so simplicial sets is a simplicial model category. So firstly, it's a Cartesian closed category. It's enriched over itself, and so that's where these tensors and cotensors are coming from in the enrichment. The model structure we've alluded to all along. The cofibrations are the monomorphisms. The weak equivalences are these weak homotopy equivalences, which are maps of simplicial sets whose geometric realizations are weak homotopy equivalences. And the fibrations are the Kahn fibrations. And we've made use of this special compatibility property that's encoded by this axiom several times, in particular when we were discussing the fibered path space factorization and its properties. Okay, the infinity category it presents, is called S. That should be a math cal S. I'm not so good at writing that on the board, so, but I'll do my best. Is S the infinity category of spaces? And this S plays a role in infinity category theory analogous to the role played by sets in one category theory. So S is kind of the base for infinity category theory, like the category of sets is the base for one category theory. But there's a sense in, and maybe what do I mean by that is, well, firstly, every ordinary category modulo size issues is enriched over sets. That's similarly true for infinity categories over spaces. You can really, by representability, you can develop a lot of one category theory in sets, similarly a lot of infinity category theory involving spaces. But there's a sense actually where this infinity category of spaces is better behaved than the one category of sets. Egbert alluded to it in his lecture series, so I'm happy about that. And it is the following. But this spaces is even better. And what makes it better is it satisfies the following definition, which in this form I think is due to Charles Rusk. So a model category such as E, you can think about maybe the E simplicial sets that presents the infinity category of spaces, has what's called descent, has descent if, so there are two parts of the axiom. The first one is sometimes called universality of colimits. So if homotopy pullback preserves homotopy colimits, preserves homotopy colimits. I guess maybe a thing to note is that in this, one thing that's special about this infinity category of spaces is that homotopy pullback is a left adjoint as well as a right adjoint, so that there's a little bit more to say because you have to kind of account for the homotopy aspect, but that might make this seem believable. And then there's one additional condition. So given a natural transformation between diagrams valued in E, of diagrams in E, and I need it to have the following property that I'm just going to explain in a picture. So on the top, let's say I've got my diagram, it's got some objects and some morphisms. The shape of the diagram is completely immaterial. And on the bottom, I have another diagram. It's a diagram with the same shape, so I can kind of draw them in parallel. And a natural transformation then, of course, is given by the data of components, like this. And my condition on the diagram is that each one of these squares is homotopy pullbacks. So I might indicate that in symbols by using my pullback symbol and then, putting a little tilde to mean sort of it's the homotopy version of pullbacks, not strict pullbacks. So in a model category, I'm going to be able to form the homotopy colimit. I could form the homotopy colimit of the top and the homotopy colimit of the bottom. Like ordinary colimits, these are just objects in the category. And like ordinary colimits, there's a colimit cone, which would look like this. So here's alpha j, yj. So these top and bottom are the legs of the colimit cone. And then having a natural transformation alpha is going to introduce a map between the homotopy colimits. And the condition is that these squares are, again, homotopy pullbacks. So that's the other version of descent. And if this is something that's new, it's a bit mysterious, and there are other ways to think about it that might be nice to explain, but it's a very convenient property. Egbert kind of appealed to it on a few occasions. So there's something like this that holds for sets as well, but you have to put restrictions on the type of maps involved in the diagram. What's wonderful about spaces is that this is completely unrestricted. Okay, so now that we have, this is, so I guess when Charles Rusk isolated this convenient property of the infinity category of spaces, there's sort of a natural question, which is what other infinity categories have descent? So this is super cool for proving theorems. So you might want other examples. Are there any other infinity categories then spaces that have descent. And there's a natural example you would turn to, which would be, so S is an infinity category, spaces has descent, so diagrams in spaces might also have descent. So that's the next topic. I'll call it simplicial presheaves, but the contravariance here is completely immaterial. So since S, my infinity category of spaces, has descent, so should, I mean really does, the infinity category of D-shaped diagrams in S. And had I explained for you what limits and colimits are in an infinity category, it is possible to define them sort of natively on the infinity category level without appealing to presentations, then this would follow immediately, because in these functor categories, the limits and colimits are all defined pointwise, so whatever exactness conditions are true in sets, or simplicial, spaces would also be true in this diagram category. However, I did not take that approach to discussing limits and colimits. Instead, we're focusing on presentations by simplicial model categories. So this leads to the following question. Is there a simplicial model category that presents this infinity category? Is there a simplicial model category that presents this infinity category? And maybe I should be a little bit more clear about what sort of thing I mean by D. So if we're focusing on presentations, I might say D is a small simplically enriched category. So we've we've seen that strictly enriched categories can present infinity categories. Since I'm mapping out of it into a con-complex enriched category, it doesn't matter so much that its spaces are con-complexes. If they're simplicial sets, it's kind of okay. As a small simplically enriched category. Okay, so I don't know. Let's think about that. So, there's a special case of indexing category D that would be easy to answer. So if the category D were discrete, or let's maybe just take the set of objects inside the indexing category D, whatever that happens to be, then the category of D-shaped diagrams of simplicial sets is just the product of the category of simplicial sets. And this, sure enough, gets a simplicial model structure just taken from the simplicial model structure in simplicial sets. So, so this inherits so everyone says pointwise, but maybe component-wise would be clearer. Pointwise simplicial model structure. What I mean by that is, to define a model category structure, I need to say what the cofibrations, weak equivalents, and fibrations are. Here, a morphism is an ob-D index family of morphisms in simplicial sets, so I just declare it to be a fibration, for instance, if and only if each component is a fibration. So, okay, that's not the case of greatest interest. We're maybe more interested in letting D be an arbitrary small simplically enriched category. And there is a relationship between these. So there's a forgetful functor that just takes a simplicial natural transformation to its components. For later use, I'll mention these have left and right adjoints. And so one thing we could try to do is just lift the whole model structure along the forgetful functor. So we could, maybe a guess is we define the model structure here. So in the simplicial presheaf category, also pointwise, just lifting the classes that did give us a model structure in this context. But there are two problems with this that are related. So if I just attempt to use the component-wise cofibrations, component-wise weak equivalences, component-wise fibrations for my simplicial model structure, one problem is that the trivial cofibrations will not, in general, will not necessarily lift against the fibrations. And exactly the same thing would be true for the other weak factorization system. So I realize I left this weak factorization system thing as a black box, but part of what it entails are lifting properties between the left maps and the right maps in both cases. And in both cases, there's a problem. If my timing is right, I'll say more about that a little bit later on. Another failure is that if I look at the mapping space between two presheaves, so B and X now live in here, so this is the mapping space in sort of simplicial sets diop. So this is defined by an enriched end of the component-wise mapping spaces. And this is not necessarily a concomplex even if B and X are pointwise cofibrant. And these are kind of related issues. So we need to modify our construction in such a way that will solve both of these issues at once. So what is this modification? So I'm just going to have to introduce some terminology. So we'll introduce the following definitions. And this works more generally for any functor U where N is already a model category. N is a model category. So we could attempt to lift the classes in a model structure on N to M in the following manner. I can define the U cofibrations to be the set U inverse C, just lifting the cofibrations from N. I can define the U weak equivalences to just lift the weak equivalences from N to M. So this is U inverse of the class of weak equivalences. And I could define the U vibrations to be just lifting the vibrations from N. So in general, these three classes will not give a model structure on M. And the reason is some failure of lifting property. So a way I could try and get around that failure is I can define the projective, sorry, maybe I'll write it over here. So the projective cofibrations, these are the things that need to lift against the trivial cofibrations. So I'm going to define them to be the things that have the lifting property that lift on the left against the sort of U inverse or the U trivial vibrations. So those maps that are both U weak equivalences and U vibrations. And I could dually define the injective vibrations to be the class of maps that lift now on the other side against the U trivial cofibrations. So the maps that are U cofibrations and also U weak equivalences. And in good situations, these three classes define something called the injective model structure. Injective model structure. While these three classes, so I'm keeping the U weak equivalences in both, define something called the projective model structure. So just, given three classes, it's not guaranteed that they give a model structure, but what I'm mentioning is that there's a theorem that, at least in the context that we're interested, so the category of simplicially enriched presheaves valued in simplicial sets has both the projective and injective model structures. And injective model structures. So there are two. What I'm indicating is that there are two different ways to solve the problem suggested here. I can take two of the classes to be just component-wise, but then I have to, this is going to be a more restrictive right class, so there'll be fewer injective vibrations than pointwise vibrations, and this is a more restrictive left class, so fewer projective cofibrations than pointwise cofibrations. I'm not going to say anything about the proof of this, but if you want to ask somebody, Lynn Moser is an expert, has a very nice paper on this topic. Okay, so now it seems like we've kind of oversolved our problem. So we were attempting to find and both of these are simplicial, and these are simplicial model categories. So they inherit the simplicial model category structure from the simplicial model category structure in simplicial sets. Now, it appears that we've oversolved our problem. We were looking for a simplicial model category that presents the infinity category, which is just d-index diagrams of spaces. We now have two simplicial model structures, and indeed both of them present the same infinity category. So these model categories are what's called Quillen equivalent. So that's the notion of equivalence for model categories. It's kind of worse than most notions of equivalence that you're used to. In particular, there's a sense in which it's not symmetric. So what I mean is I could consider the simplicial presheaf category given the projective model structure, and I could also consider the simplicial presheaf category given the injective model structure. If I'm looking for comparison functors between them, I might use the identities, because it's literally the same category. But I've indicated this adjunction pointing in a particular direction because between model categories, the requirement is that the left adjoint preserve the left classes, while the right adjoint preserves the right classes, and that only works in this one direction. Nevertheless, when I descend to the level of homotopy categories, the homotopy categories here are equivalent. It's the same weak equivalences after all, and so that's the sense in which these both present the same infinity category. So both present the infinity topos of spaces. Okay. So I think now, so I keep accidentally saying infinity topos, so I'm finally going to tell you what that is. And again, this isn't the definition of infinity topos that you would see in higher topos theory, Jacob Larry's book, for instance, but it's a notion that will be particularly relevant to modeling homotopy type theory. And this is something called a model topos. And this form of the definition is due to Charles Resk, but inspired by previous work of Carlos Simpson and Cohn and Berzosi. This definition is actually a theorem in his paper, and he uses a different definition, but I'm going to reverse the order of those two things and mention them. So here's the definition. So a model category E is a model topos, in his terminology, so there are two requirements. One is that E has a small presentation, and I need to explain what that means, and I will momentarily. This is in the sense of Dan Duggar. And the second one is that E has descent. So this kind of descent special property is sort of really central to model toposes. These are the model categories that present infinity toposes. And one thing I should mention somewhere, the notion of topos that I'm referring to all along is kind of the Grothendieck style topos as opposed to an elementary style topos. So the infinity toposes in Mike Schulman's theorem are the sort of Grothendieck style toposes. Okay, so what's this small presentation business? So a small presentation for E is given by Aquilon equivalence. Between E and simplicial presheaves, but I'm allowed to modify this category of simplicial presheaves by localizing at some set S, where I've localized at some set S at S. So for our purposes, it's going to be completely immaterial sort of what direction this Aquilon equivalence goes. So Duggar is more precise about this in his work than I'm being here, but we don't need that extra precision, so I'm not going to bother. Where I've localized at S, what does that mean? So a localization, for the experts, these are the left Bausfield localizations of a model structure on a category E is a model structure on the same category, with the same cofibrations, more weak equivalences, and fewer fibrations. And the idea of it, the name comes from localization and ring theory, is that I'm formally inverting the maps in S. So S should be a small set of maps in the category that are not already weak equivalences, because otherwise this is trivial. And what I'm doing is I'm formally adding these to the weak equivalences. That's why I have more of them. And for that to balance out, it's necessary to have either fewer cofibrations or fewer fibrations, and we're doing it on that particular side. That's the sort of leftness and left Bausfield localization. There is a dual notion, but it's kind of less common, and in any case won't be relevant here. Okay, so what we're really interested in is this notion of a model topos. So what we've seen is that if it has a small presentation, then that already characterizes these categories up to equivalent equivalence. They have to be model categories of simplicial presheaves, localized at S. In fact, I could use either of these model structures because they're equivalent equivalent and the localization respects that, so it kind of doesn't matter, though I will have a preference in a moment. But then this second condition, this descent condition, imposes an additional requirement on the localizations. So not all model categories satisfying 1 will also satisfy 2. Those that do, I guess, are described in this following theorem, also due to Resk, is that, so E is a model topos if it is what's called a left exact localization. So if it is equivalent equivalent to a left exact localization of simplicial presheaves. Here, let me go ahead and just say the injective model structure, because that's the one we're going to want to use going forward at some set S. And I then owe you a definition of left exact, but what that refers to is that there's always going to be a comparison. If I localize any model category, the identity functors always provide a comparison between the original model structure and the localized one. And because the left adjoints have to preserve the left classes, the identity goes in this direction. The left adjoint identity goes in this direction. And the requirement is that the left adjoint of this localization preserves homotopy pullbacks. So where the left adjoint, so this is explaining left exact means the left adjoint preserves homotopy pullbacks. So this adjunction will be something called a Quillen adjunction, meaning that the left adjoint always preserves homotopy colimits. You could imagine that if it preserves homotopy pullbacks, in addition, then these conditions, which are about the relationship between homotopy pullbacks and homotopy colimits, would be well behaved, and that's kind of the idea. Okay, so what we have on here are two different perspectives on model topoi. On the one hand, it's sort of small, some size condition, and then descent. On the other hand, this is an explicit characterization. We can take a particular family of model structures, these so-called injective model structures on simplicial presheaves, and then localize at a class S. Okay, so now I finally get to talk about homotopy type theory, but any questions about that first? Yeah. Yes, either way. Well, both of you can do it. Well, somebody go first. Yeah, that's a great question. There's a sense in which the growth and decay fibrations are sort of more fiddly than the model category fibrations. It's not so far off. What I mean about that is they're not closed-end retracts, if I remember correctly. So these are sort of even better fibrations. The name and the inspiration really comes from topology. So what these model categories are for is it's kind of an abstract way to do homotopy theory. This is absolutely the same root. This was based up. So
I mean, they both come from topology, but it's not like.
I don't know the history of that notion, so I can't comment. But it's not so far off. So
your notion category is more general than what
right. So I mean, kind of, but barely. So I mean, for me, in the world where I live, like all model structures are combinatorial or are based on a locally presentable category, in which case these are the presentable infinity categories. I'm sure that's not exactly true, and there might be an expert in the room who could tell more about that. But. No. So every infinity category is presented by a model, or sorry, not at all, presented by a simplically enriched category, but being presented by a simplicial model category means you have all limits and colimits. So that's really the thing to think about. If you don't have limits and colimits, you're not being seen. here, but you wouldn't be a topos, so we're okay to leave those out for today. So all ordinary 1 categories are infinity 1 categories. If you don't have limits and colimits, you're definitely not in this worldview. Okay, so there's a lot more to say about model toposes and infinity toposes. I apologize. I sort of overwrote the lecture notes for this section, so there's some discussion there about the relationship with ordinary 1 growth-indic toposes, but I really want to get to the end, so I'm going to move on if you don't mind. So what I want to tell you now, so now we're going to start talking about Mike Schulman's paper, and everything that follows is going to be a theorem or a definition due to him. And this is one of those papers where the definitions are as interesting as the theorems, and it's really beautiful. So the first definition he gives is something called the type theoretic model topos. And you'll note the similarity with that terminology of RESC, and we'll have more to say about that in a moment. But let me just start by giving the definition. So a model category E is a type theoretic type theoretic model topos. Model topos if. Okay, so the first requirement is that it's underlying category. So model category is in particular a 1 category. That's the connection with the thing we mentioned right away. Model categories are really just 1 categories, but then you add some other stuff. So its underlying category is a growth-indic 1 topos. Is a growth-indic 1 topos. So again, the notion of topos that we're using everywhere today is this growth-indic topos. So these sheaf toposes, I guess we can see this here, this localization, I should have mentioned that, gives you fewer fibrations, so fewer fibrant objects. So it's imposing some sort of sheaf condition on the fibrant objects. Kind of like what Simona Pali was referring to with the Siegel condition in her talk yesterday. That's an instance of the sort of localization that's commonly performed. Okay, so it's underlying, though that's not an infinity topos, but whatever. All right, so its underlying category is a growth-indic topos. Its model structure, so as a model category, its model structure is simplicial, so combinatorial. This is a technical size condition that I won't unpack. But yeah, this is some sort of size condition, and this will make the infinity category presentable, if you know what that means. Simplicial combinatorial, right proper, though it will also turn out to be left proper. So that's something. And then with the cofibrations exactly equal to the monomorphisms. And maybe one thing to point out, back here I mentioned that there were 2 different perspectives we could take for a presentation of the infinity category of diagrams and the infinity category of spaces. And the reason for preferring the injective one everywhere is this is the one that keeps the pointwise defined cofibrations. So we'll have the monomorphisms as the cofibrations. And because that's something that's very nice to have in type theoretic models, that's our reason for preferring injective to projective. Most of the literature actually has the other choice. Okay. So then it's simplically locally Cartesian closed. So as a 1 topos, it's a locally Cartesian closed category. So what simplically locally Cartesian closed refers to is that those adjunctions are all simplically enriched adjunctions as well. And then the final condition is that it has a locally representable and relatively acyclic notion of fibered structure. Okay, so there's a whole bunch of stuff in this last definition that I need to define for you, and I will, but let's just black box this for now. So these are the sorts of hypotheses we've been introducing along the way for the model categories that support models of type theory. We're adding now some funny one at the end, and I'm going to say a lot more about that momentarily. Okay, but what's the point of having this new abstract definition? Yes? So it's automatic that left Gauss field local. So absolutely. So Steve is pointing out correctly that in a model topos, we would like the localization functor, the left adjoint, to preserve all finite homotopy limits. So that's absolutely correct. For left Gauss field localizations, though, I believe that the preservation of the terminal object is automatic, so that you get finite homotopy limits by just asking for homotopy pullbacks. And if I'm wrong, then Steve is right. We definitely do want all finite limits. He's happy? Okay. So, great. Okay, so the point of this abstract definition is it gives us a convenient way to state the main theorem, which is the theorem that everybody wants. So any type theoretic model topos, type theoretic model topos has a model of homotopy type theory, has a model of homotopy type theory with, so kind of all the types, all the usual types. So this models the pi types and the sigma types and the, I don't know, what are the other types? Coproducts, products, things like that. The terminal type, the unit type, and also, things like the natural numbers and your favorite CW complexes, or favorite maybe finite CW complexes like S1. So Mike is much more precise in the paper about exactly what's included here. So if you're unhappy with all the types, look at his paper instead. It also has as many univalent universes as there are inaccessible cardinals, as there are suitably large inaccessible cardinals. And it finally also has higher inductive types, many higher inductive types, but the reason for distinguishing between certain types that are in this model and other types that are in this model is the universes are closed under the type forming operations, the logical operations in 1, but it's sort of not known about 3. So there's kind of one open piece of the puzzle, which is certain constructions of higher inductive types. It's not yet known whether they stay within the same universe level, whether they increase the universe level. So there's a lot more discussion about that in the paper as well. Yes? That would be a great topic to ask Egbert. But well, here's an example of a higher inductive type, though it's a very simple one. So in an inductive type, you sort of freely say, I want my type to have certain terms. And in a higher inductive type, you're also allowed to freely add paths, so identifications between terms, and also paths between paths and paths between paths between paths. And there are sort of small, simple ways to do that, which would build these like finite CW complexes. And then there are kind of much more sophisticated constructions that would give like propositional truncation, set truncation, K truncations, and it's, but it's a very new, this is not something that was traditionally part of Martin-Liff type theory, and I think the semantics are a bit less well understood, and that's partially why there's a little bit of a distinction here. Okay, great. So I should say a warning here. Sort of we need a coherence theorem, So remember, a model category, one category, even the best behaved model category, when it sort of models certain type forming operations, what it means is it has categorical analogs of those constructions. Maybe it's a push forward in case of modeling pi types. And then there's some stability property that would be easy to express categorically, that if you pull back, then the results are sort of isomorphic. To make it into a genuine model of type theory, we need to strictify everything. So have strictly stable pullbacks that strictly respect all of the type forming operations. So Voevodsky's solution to this coherence problem used this device of having a universe in the category. So we described how a universe in simplicial sets can use to be built a contextual category that then does have this strict stability. Since Voevodsky, there have been more modern approaches to solving this coherence problem. And the one that Mike uses is due to Peter Lumsdaine and Michael Warren. It's called Local Universes. It's really beautiful. Highly recommend checking that out. But I'm not going to mention it. But what's nice is that there's sort of better machinery for dealing with these coherence problems today. So that solves it using a different categorical model of type theory than the one that I've discussed. Okay, so this is great. Maybe another thing that I can say, though, is that, this is all well and good if you had any reason at all to care about type theoretic model toposes. So I have to say a lot more about that. So one thing to observe is that any type theoretic model topos has descent. Theoretic model topos has descent. So the first of the two descent axioms is not so hard to prove just from the parts of the definition here that are easy to understand. The second axiom relies very heavily on the meaning of this notion, which I haven't explained yet, so I'm not going to say anything about the proof. But as a corollary, any type theoretic model topos is a model topos in the sense of RESC. Model topos is a model topos. And the proof of this, well, what do I need for it to be a model topos? I need it to have descent, and I need it to have a small presentation. And there's this theorem of Duggar that says that combinatorial model categories have a small presentation. Combinatorial model categories have a small presentation. So, all things considered, this really isn't so bad. So what have we achieved? So we have this new axiomatization that is sufficient. So these axioms are sufficient for giving an interpretation of homotopy type theory. That's pretty cool. We've seen that these axioms also imply that your category is a model topos. That's pretty cool because that sort of suggests some sort of a connection to infinity topos theory. But we really want to result in the other direction. We have all of these examples of model toposes, and we don't yet know that any of them are type theoretic model toposes. Well, maybe secretly we know about one, but before I do that, I desperately need to explain to you what this condition means so we can start building examples. So the whole rest of the talk will be building examples of type theoretic model toposes that will be sufficient to cover all model toposes, and that's the main theorem, that any infinity topos has an interpretation of homotopy type theory. Okay, I've got to erase a big board, so any questions in the meanwhile? Yes? Yes, my view is that saying that HOT is an internal language of something would be a stronger statement, and that has not yet been proven. Part of that statement would imply that there is an interpretation, and that's what we understand so far. It is not the expectation, though, that homotopy type theory is the internal language of model toposes or infinity toposes. Really, the expectation is that would be true when you extend to a broader class, including these elementary infinity toposes. So there are some special things about these type theoretic models. So these always, what is it? Now I'm forgetting. Well, anyway, so this is not meant to be the fully general case, but because elementary infinity toposes are much less well understood than Grothendieck style infinity toposes, I'm not going to say anything about that, though you could ask Nima if you wanted to, Nima Rasek, who's here. Okay, great. So because of this theorem, I would really, really, really like to have some examples of type theoretic model toposes, because then I could get a model of homotopy type theory. In order to do that, though, I need to explain this fourth axiom that is sort of chock full of terminology that we have not introduced. So this next section is going to be on notions of fibered structure. And what this notion of fibered structure is all for is it's for constructing the universes. So we've seen secretly one example of a notion of fibered structure. And I'll start by reviewing that example. And if you thought that I was presenting that in a frustratingly abstract way, this is why. So this is on notions of fibered structure, So previously we discussed what the fibrations in a model category formed. So let's let E be a model category. Please feel free to think just about simplicial sets. So we had this groupoid valued pseudo-functor that I was writing as Blackboard bold E that takes an object in E into, well, first you form the slice category, and then you just restrict to the subgroupoid in the slice category, so the isomorphisms here, and the action was by pullback. And so if the fibrations in my model category are called F, then there is a subfunctor in here, which we wrote as Blackboard bold F, which is kind of the fibrations and their pullback actions. So this sends B to the full subcategory of fibrations over B. Or sorry, again, I want to take a groupoid, so that's the intention here. Okay, so the inclusion here, so both of these are pseudo-functors from E, contravariant on E, into groupoids. So the inclusion, that's just where these things live. Sort of in this category of groupoid valued pseudo-functors on E has the following properties. So the first thing to note is, so this category that we're working in is secretly a two category. The objects are these groupoid valued pseudo-functors. The morphisms then should be pseudo-natural transformations, so it's a bit weaker than the usual notion of natural transformations. But this is actually a strict natural transformation because we're just kind of including a sub-object. This is getting its pullback action just inherited from this. So the first thing is that this is a strict natural transformation. If you don't know what a pseudo-natural transformation is, then I invite you to ignore this first condition. But the second one, which is maybe more important, is that this is a component-wise discrete fibration. This is a component-wise discrete fibration, and now I really do mean in the sense of growth and decfibration. So discrete fibration. So what do I mean? So if so component-wise discrete fibration. So if I, plug in an F to each of these functors, this is F to be E over B. So this is the groupoid, of groupoids. So this here is the groupoid, which is just the slice category, but taking only the isomorphisms, and this is this subgroupoid. And what does discrete fibration mean is that if I have any map downstairs, so that's a pullback square, and a lift of the domain upstairs, that means that the right map in the pullback square is a fibration, then there exists a unique lift upstairs, which in this context means that the fact that this is a fibration makes that a fibration as well. So this is kind of a funny sort of discrete fibration because it's also an inclusion. That's not the typical sort of discrete fibration. But in this context, all this is saying is that the fibrations are a pullback stable class of maps in E. And that's essentially the definition of a notion of fibered structure. So now what I'm going to say is we're going to keep E as this core of self-indexing, but let F vary. So I'm about to introduce a definition that involves both an F and an E, and I want the E to be this E, but I don't want the F to necessarily be this F. F is going to be something more abstract. The F that I had used previously is an example, of course, though, which is why I'm using such similar notation. So here's the definition. So a notion of fibered structure is a strict discrete fibration we'll write it as F phi to E. This is in this category of groupoid valued pseudofunctors on E with small fibers. Okay. So in particular, this is one example. What on earth does this actually mean? So here, sort of the idea is that if I take an object downstairs, so for each, an object downstairs would be like an F, a morphism from E to B. So this is in EB. The set FB is the set of what's called F structures on F. So F structure could be read as fibration structured. We're thinking sort of more structurally about the notions of fibrations. In this sort of example, the fibers were either empty or singletons. So that means any morphism F either was a fibration or was not a fibration, and there's kind of nothing more to say. But in general, there might be multiple witnesses to the fact that F is a fibration, and that's what this FB, the set of F structures, is. So a chosen F structure makes F into what's called an F algebra, makes F an F algebra. And the discrete fibration property behaves as follows. So we have this discrete fibration of groupoids, F of B over E of B. So a morphism downstairs, I'll draw the same diagram, but I'll decorate it a little bit better, would be a pullback square like this. Morphisms in this category are given by pullbacks. Now, a lift upstairs would be sort of F algebra F. So giving this F an F structure. The discrete fibration property says that then if I have any pullback of an F algebra, G gets an F algebra structure. An F algebra structure, in which case this pullback square is called an F morphism. So what this notion of fibered structure is providing is a notion of F structure for an arbitrary map, where the idea is that something should only admit an F structure if it's a fibration. I'll tighten up that connection in a little bit. So if you choose an F structure, that makes you an F algebra, and the property of these F algebras is that a pullback then it would induce an F algebra structure here from an F algebra structure there. This is similar to something that we've observed a few times, which is that if this map F is a fibration, then G becomes a fibration by the universal property of pullback. This is a reflection of that sort of thing. Okay, so Mike gives us a whole bunch of examples, but there are only a few that we really need, so I will mention those briefly. So the first example of a notion of fibered structure is the one that we had seen previously. So for any model category, the fibrations define a notion of fibered structure just as a pullback stable class. Or maybe more generally, I could say, so a full inclusion, that's also a discrete fibration. So that was the scenario we were in previously when discussing the simplicial model, is called a full notion of fibered structure. And the data that this actually gives is just a pullback stable class of morphisms. This is a pullback stable class of maps. So nothing too complicated going on there. But as I was indicating, these notions of fibration can be a little bit more structured, and I'll give an example that illustrates that. So if I'm given a functorial factorization on E, factorization on E, so what that entails is firstly, for any morphism F in E, there's a specified way to factor it. So I'm giving names to the left and the right factor because those are the names of the functors. The composite then has to be this F. And then what would make it functorial? Well, you know what, I guess that doesn't actually matter, so I'll not mention that. So given a notion of functorial factorization, we can say an RE algebra, E being the name of that functor, structure on F is, so whenever I have a functorial factorization, I can rearrange it into a lifting problem as follows. So there's, in fact, two ways to do this, but this one I'm going to have F lift against its left factor. And the data of a specified lift here is a notion of F algebra structure. So if this is the functorial factorization for the trivial cofibrations and fibrations in a model category, then this would be a structured way of thinking about the fibrations. But the reason we'll be interested in this notion of fibred structure is that you can apply it slightly more generally to a functorial factorization that is not precisely one of the ones coming from a model structure. So there's another example of notion of fibred structure which is relevant, and this has to do with sizes. So if cap is a regular cardinal, maybe I'll say cap is a sort of sufficiently large regular cardinal, because for this to be well behaved with respect to some other stuff that I'm going to say later, I need it to be kind of a lot larger than the size of the locally presentable category, but I really don't want to get into that. Then we could have another example of one of these full notions of fibred structure here, where these are in the terminology I used last time, these are the kappa small maps. What that really means is relatively kappa presentable, which means that pullbacks along any kappa presentable objects are kappa presentable. This again is one of these full notions of fibred structure. And then the final example is that if I'm given two notions of fibred structure, so say an F1 and also an F2, both notions of fibred structure, I could form their pullback in this category. So just the pullback over E. I mean, these are objects in some 2 category. And this is, again, a notion of fibred structure, is a notion of fibred structure. So in this case, and sort of F1 cross F2 algebra structure is a pair given by an F algebra structure and an F1 algebra structure and an F2 algebra structure. There's an F1 algebra structure with an F2 algebra structure, and there's no required interaction between them. So this is very useful. So for instance, if I wanted to use one of the notions of fibred structure that I mentioned over there, but also impose some sort of size criterion, I could form a pullback, and that's going to accomplish that. Okay. So my goal right now is to explain the missing hypotheses and the definition of a type theoretic model category. What I've explained so far is the notion of fibred structure that's referred to there. There are 2 technical conditions, and where they come in is to build a universe out of a notion of fibred structure. And I'm going to start by just explaining what that means. So a universe for a notion of fibred structure F, of fibred structure F is, so firstly it's an F algebra. So what does that mean? So that's, again, a map in the category E, but I've chosen an F structure for this map. So it's an F algebra. So by the bicategorical Yaneda lemma, once I've specified an F algebra, then there's a map from the representable at U to this notion of fibred structure F that just picks out the F algebra given by this pi. And the condition is that this is, an acyclic fibration in the sense that we've seen previously. So for all cofibrations in the model category, so I should be in a model category. Let E be a model category. So if I take an arbitrary cofibration I in my model category, I can look at the lifting problem presented by these representable functors, and here's the map I, and then these 2 maps are allowed to be arbitrary. And the requirement for being a universe is that I have a lift in here. So this is this somewhat mysterious condition that we have seen before. So So let me unpack it, and the unpacking is going to be exactly the same as before, except previously I was saying fibration in various places, and now I'm going to say things like F-algebra and F-morphism. Let's see this unpacking. So this, you might remember, implies in particular that the universe is a weak classifier for all F-algebras, having this kind of F-algebra structure. And this technical condition was used then in the verification of things like the fibration extension property, which reflect the fibrancy of the universe, and also the equivalence extension property, which is the univalence of the universe. So what does this mean explicitly? So this bottom map here, P, is an F-algebra with codomain B. So given an F-algebra P, so that's part of the data presented by a lifting problem. So I'm going to depict this P as if it's a fibration, but what I really mean is it has a specified F structure, so it's an F-algebra. Then this top map is given by the data of a morphism from A into the universe. So here's my other F-algebra pi, here's my H. So commutativity of this triangle says that when I pull back P along I, I'm going to get a map here, D, and this map becomes an F-algebra and an F-algebra morphism because the composite is into this pseudo-functor that represents the F-algebras. And then I require that the back part of the diagram is also an F-morphism. So these two things are both F-algebras. Their pullback needs to define the same F-algebra structure on this Q. Then that lifting property says that there exists a new pullback square in the front that is also an F-morphism. So this has to be also, maybe I'll just say everything an F-morphism. Everything an F-morphism between F-algebras. So for full notions of fibered structure, I could just say fibration everywhere, and it's exactly the same notion we've seen before, but there's a more structured version of this in full generality. Okay, so now I'm going to start to define these hypotheses and explain what they're used for. So the first definition is an F structure. So an F structure, or a notion of fibered structure. A notion of fibered structure is called locally representable. Is locally representable. So one of the two hypotheses I need, if for all morphisms F from X to Z, so recall that the data of a notion of fibered structure is really this F together with a discrete fibration to E, the core of self-indexing. So because F here is just a morphism, that means that there is, by the innate lemma again, a map here that picks out that particular morphism with codomain Z. So in the category of kind of groupoid valued pseudo-functors, I can form this pullback. And the condition is that this pullback is representable. So if for all Z, P is representable. So it's equivalent to maybe, I guess, isomorphic to something here. So this is a very neat definition, and I'll suggest it as an exercise to unpack it because, it gives a nice perspective on what an F structure really is. What I suggest is apply this universal property, map in from a representable, and unfold what it's saying. But our use of it is going to be as follows. So let E be sort of combinatorial model structure on a growth-indique topos, on a growth-indique topos with the cofibrations equal to monomorphisms. Maybe I need right properness. I've forgotten. No, apparently not. Then any locally representable, and then I need a size condition and small groupoid valued, I guess meaning that the values are sort of essentially small notion a fibroid structure has a universe. Structure has a universe. So you might recall in the simplicial model, we had this locality condition. We said that the fibrations are local, which means that they're detected by pullback to representables, and that was used in a key way in the construction of the universe. This is very similar. This locally representability is the analog of the locality condition. So the proof is this universe is constructed as a cofibrant replacement of the fibroid structure F. So kind of examining this diagram to say that this is a trivial fibration suggests, if you sort of know a lot of model category theory, that this might be a cofibrant object, and this is the sort of cofibrant replacement of this map. So there's a standard technique in model category theory for constructing cofibrant replacements or functorial factorizations more generally, called Quillen small object argument, and that's essentially the construction used here. The way that these hypotheses feature is to show that this F, when regarded as a functor from EOP to groupoids, it preserves cell complexes. So all of the size, so cell complexes are colimits. A functor of this form would not commonly preserve colimits, but when these cell complexes are, by cell complexes I mean coproducts and pushouts and transfinite composites of monomorphisms. And these size conditions that are all kind of impacted here guarantee that those are carried to the corresponding weak bicategorical limits, and that's what makes Quillen small object argument work. So that's a very high-level description of that. So what I haven't explained at all is like what this notion of fibroid structure has to do with the fibrations, and that's going to be the final piece. So a question might be, what does F have to do with fibrations? So again, what a notion of fibroid structure is it's some map between these groupoid valued pseudofunctors. This is sort of the family of all maps in E under pullback. This is the family of, F algebras in E under F morphism. It's kind of abstract. Usually we think of the fibrations as being a sort of pullback stable class of morphisms, so really that should just be a sub-object of this. And what you could construct in general is the image factorization. So this is going to be a full inclusion, and this is going to be a surjection. So this is the image factorization. And the idea is this is now a pullback. So the image of the F algebras, these are the maps that admit an F structure. So something in here is an F algebra, so it's something with a specified F structure. When we take the image, we're forgetting the F structure, and we just, it's not necessarily going to be surjective. Not every morphism admits an F structure. This is the sub-object of the morphisms that do admit an F structure. Sort of morally, these are going to be the fibrations, assuming that the F algebra structure has something to do with fibrations, which will be a requirement. And this is the context in which I can define the final notion that appears in the definition of a type theoretic model topos. So a notion of fibroid structure is relatively acyclic. Of fibroid structure is what's called relatively acyclic if, when I do this image factorization business, I again get one of these trivial fibrations. So here's the quotient from my notion of fibroid structure to its image. And again, it's exactly going to say that for all cofibrations, I can look at the induced map between representables, and I have, once more, a lifting property. So this can be unpacked in the same way, though I won't do so. But the point of this is, so in a relatively acyclic notion of fibroid structure, I have some sort of trivial fibration in the sense of having a lifting property against these monomorphic, or the cofibrations. In a universe, I also have a trivial fibration. And the point is these compose. So note if F is relatively acyclic and has a universe, so what having a universe means is that, again, there's some object U that emits an F algebra structure pi, and that gives me this map to F that has some lifting property being a trivial fibration. Relatively acyclic means that if I forget onto the image, I again have a trivial fibration. And the upshot of that is that this is equally a universe for this image notion of fibered structure. So I can solve a lifting problem against a cofibration by first solving this lifting problem and then solving that lifting problem. So composing the trivial fibration structures. And now I can state my theorem about the existence of universes. So theorem, so E, maybe I'll just say E satisfying those hypotheses. So if E is a type theoretic model topos, so in particular, it has a notion of fibered structure F that is relatively acyclic, locally presentable, and now I want to ask, in addition, that its image are the class of fibrations. Then E has a universe. Well, I guess F has a universe. That's univalent, that's sort of fibrant and univalent. So all of the things that we went through last time for the universe of confibrations hold equally in this context, and this is the abstraction that lets you get there. Okay, so there's two big questions that remain. So now that we finally understand this definition of a type theoretic model topos, we need examples, and we would like our examples to be sufficiently robust to cover all infinity topoi. So what examples do we have? So firstly, simplicial sets with the Conquillin model structure. And then we also have closure properties. So it's not so hard to see that if E is a type theoretic model topos, type theoretic model topos, then the slice of E over any X is 2. And similarly, if some EIs are type theoretic model toposes, then the product of them is again a type theoretic model topos. So we want 2 further closure properties, and that will suffice to cover all examples of infinity topoi. Maybe I'll go ahead and state them as theorems now. So the first thing that Mike proves is that if E is, again, a type theoretic model topos, type theoretic model topos, in particular, that's a simplicial model category like we were discussing above, then we can look at simplically enriched functors in here with the injective model structure. And this, again, is a type theoretic model topos. So we have to take the injective model structure to preserve the property of the cofibrations being the monomorphisms. That's why I was emphasizing that previously. And then the second theorem is that E is a type theoretic model topos, and S is a set of maps so that S localization is right exact, so that localization, is left exact. Then the localized model structure, E localized at S, is type theoretic. And since the model topoi are built from simplicial sets under these 2 operations, this is going to cover all examples. So what is hard about this is that in both cases, so both of these constructions on model categories do not retain very much information on the fibrations or the fibrant objects. And in order to have a universe, we need to know what the fibrations are. There's absolutely no way we can define a notion of fibered structure without knowing what the fibrations are. So it's kind of a famously hard problem. I mean, this notion of injective fibrations in simplicial presheaves has been around since the 1980s. nobody ever had any idea what the fibrations are. This seems like totally intractable. But Mike had a new idea to solve this problem, and that's the solution to 1. The solution to 2 requires some work of ABFJ. So let's see, Anel, Biederman, Finster, Riehl. Since Eric Finster's here, I'm going to defer to him on that. And if I could have 5 minutes, I'd like to tell you about the solution to 1, and then I'll stop. So we'll be OK for lunch? Great. So this last 5 minutes, I think, is a beautiful coda because it's completely independent of anything that's come before. And it's giving a beautiful solution to kind of an old problem in abstract homotopy theory, which are what are the fibrations in the injective model structure. So even if it weren't useful to prove this spectacular corollary, that namely all infinity toposes have a model of homotopy type theory, I would be excited about this. And I just want to give a little tiny sense of what it's about. So what we're about to do is characterize the injective fibrations in simplicial presheaves. So our setting again is this functor category, so simplically enriched functors and simplicial natural transformations in simplicial sets. Let's suppose that I is a pointwise trivial cofibration, and F is a pointwise fibration. So when we discussed lifting model structures, here our first idea was to just use the forgetful functor down to the product category and just lift up all the classes. And I said that doesn't work. Let's think about why it doesn't work. So here's my I. This is a trivial cofibration, but component-wise. Here is my F. This is a fibration, but component-wise. So what that means is that if I plug in an object of D, and I have a lifting problem, presented by some Y and some B maybe, then so now these are just the components of all these natural transformations. So being a pointwise trivial cofibration, pointwise fibration, means that when I plug in an object, I get a lift, because now I'm back to a weak factorization system on simplicial sets. But if I consider what these lifts assemble into, so here I'm going to draw this diagram again, but now I'm in this functor category. So this I and Y and B and F, all of these things really were simplicial natural transformations. I have these component-wise lifts, maybe I'll call that L. But this L does not assemble into a natural transformation. Naturality fails because there are not unique solutions to lifting problems. If you just choose a solution, there's no reason that the diagram, the naturality squares would compute. However, this L is a homotopy coherent natural transformation. So the lifts assemble into a homotopy coherent natural transformation. So this is a very classical thing in a certain corner of mathematics. Homotopy coherent natural transformation, meaning that the naturality squares don't commute, but they commute up to homotopy, and in a pretty strong way. This is due to the homotopical uniqueness of solutions to lifting problems. And so if there were some way to rectify homotopy coherent natural transformations into strict ones, then we could require some additional structure of this pointwise fibration here to make a weak lift into a genuine lift, and that's the idea of the characterization. So there's a theorem that if I look at the homotopy coherent natural transformation, so that's like this lift here, these correspond bijectively to strict natural transformations out of this thing called B, F, U, F, U, X to Y, where this is called the bar construction. And they also correspond to this thing, maps strict natural transformations from X to this thing called C, U, F, U, F, Y, which is called the cobar construction. So there are these things called bar and cobar that respectively classify and co-classify simplically enriched natural transformations. So in particular, if I started with the identity, homotopy coherent natural transformation, I'd see that I have a natural map BF UF UX called epsilon down to x. And I also have a natural map, which I'm going to call nu, which goes from y to c of u, fu, fy. And so I can imagine, let's try and fit something like this into this diagram. I'm going to redraw it again in the special case where there's a terminal object down here. So this nu kind of lives halfway, c, u, fu, fy. So nu is this map right here. I've factored the lifting problem down to the terminal object halfway through. The idea is that the pseudo-natural transformation L will give me a strict lift kind of halfway up here. And if this map had a retraction, or sort of dually, if this map had a section, I could use that retraction to lift all the way up. And so what this suggests is that a characterization of the injective fibrant objects might just be pointwise fibrant objects, so that I have this retraction here. And that's exactly the idea of the solution. So then the last thing I'll say, I know I said 5 minutes and it takes 7, so apologies. That's how the whole thing goes. So what is this bar and cobar? It's a really beautiful thing that relates to something called the free adjunction. So this is a fun bit of two-category theory. So there's a two-category called ADJ, which is the universal two-category containing an adjunction. So as a two-category, it has two objects, which I'm calling plus and minus, and then 4 Hom categories, which I've drawn in this cartoon. So these are familiar, if you're familiar with sort of simplicial homotopy theory, and if not, that's fine. They are what they are. The theorem says that adjunctions correspond to 2 functors out of this 2-category into wherever. So if, for instance, I had an adjunction, I would get a corresponding 2-functor that sends minus to where the monad lives and plus to where minus to where the comonad lives plus to where the monad lives. And then as a 2-functor, it gives actions on the 4 Hom categories. So these are the Hom categories inside ADJ. This is on the monad side, the comonad side, and the 2 that go across. These then map into the corresponding functor categories. And you can see they just pick out all of the free adjunction data. So as a functor from n to n, I have the identity, but also the monad UF and also UF. I have all of these natural transformations in here. And they assemble into a diagram, which is a co-simplicial object. So this bar and cobar seem kind of mysterious, but all they are is sort of the transposes of these functors. So a functor from delta plus into the functor category from n to n can equally be regarded this way. So what the version of the bar and cobar that I mentioned up there is we just take the totalization of the co-simplicial object in this case, or the geometric realization of the simplicial object in that case. And from this, Mike produces a functorial factorization that gives a relative version of the condition I mentioned there. So that's in the notes. In the interest of time, I think I'll just stop. Thank you.
Thank you very much. So I think we have time for one question, I think. One. Oh, so short questions. Then. Yeah. 2 short questions.
Thank you very much for your talk. I have a really quick question. I thought that Mike Schulman had a third condition for the fibrant notion of Aristotle, namely homotopy invariance.
Yes, that's true, and I snuck it in by requiring that the underlying class are the fibrations.
Okay, I see.
So with that requirement, then, yeah, I think I probably should have mentioned there, so that presents the fibrations, and that's how I got rid of that.
Okay, thank you very much.
Yeah.
Hi, Emily. This new approach of Schulman is completely independent by the theory of, is it a kind of generalization of a theory of minimal fibration, or it is completely different. I mean, it's conceptually different.
Right. So that's a good question. So what minimal fibrations were used to do was prove the our notion of universe suffices to tie fibrancy of the universe to this thing called the fibration extension property. And then minimal fibrations were used, which is just something about the model category. Minimal fibrations were used to prove the fibration extension property for the model category. So an observation that was made subsequently to Blavatsky's original proof by Raphael Stenzel is that the fibration extension property actually follows from the equivalence extension property. So once you have that, you can kind of skirt around the minimal fibrations. I think there's maybe a high-level sense in which they're kind of being abstracted away in these axioms, but it's really pretty indirect.
So thanks again.
No.